All right, welcome back, everybody. So I want to do a quick video on the fast Fourier transform, and I could make some joke about having a short video on the fast Fourier transform. Anyway, the point of this video is to tell you a little bit about the fast Fourier transform. Now, this is a topic that you see in computational physics. I'm only going to talk about it because I think it ties together our story a little bit. And it's the way that we do Fourier transforms most commonly right now when it comes to physics research, and therefore I want to show you how our notion for the analytic form of the Fourier transform connects to the thing that we really end up doing the most, which is a numerical Fourier transform, and that is really at the heart of the fast Fourier transform. So before I get going with that, I want to tell you why this topic is actually a little bit silly when we start. Because our story of developing the Fourier transform started with a discrete set of blocks and a discrete set of modes, right? And we used matrices and eigenvectors to find out what those modes were. And at the heart of that was trying to establish what part of the problem oscillated with some characteristic frequency, right? Those eigenstates represent what part of this system has a certain set of characteristic frequencies, and for this I found that a discrete set of blocks has a discrete set of modes, has a discrete set of resonance frequencies. I then sort of went to the continuum limit where I took those blocks and I said, well, we're going to break them up into smaller and smaller bits until we finally get a string. And we found that a string with boundary conditions, even though it looks like a continuous system, still only has a discrete set of modes, right? It has, and this was the Fourier series, that I had functions that described each one of the modes, but I still had a discrete set of different possible frequencies. There were an infinite number of them, so that's what was different between the blocks and the string, but there was still a discrete set of frequencies that I could use. And then I took that idea and I said, well, let's get rid of the boundaries. And by getting rid of the boundaries, I ended up in a place where now I had not just an infinite set of modes, but I had a continuous set of modes. Therefore, any value of omega was allowed. I still had a dispersion relation that told me what the wavelength was for any given value of omega, but I ended up with a set of states that defined any possible wavelength, right? So I now had a continuous set of states. I had a continuous set of frequencies, and therefore I had to develop this picture where I decomposed my system using an integral rather than a sum. Okay. And now what's so weird is when I do this numerically, obviously when I represent a function numerically or I represent data numerically, I don't have the data at every arbitrary point in time, and I don't have it from, say, t equals minus infinity to infinity, or if I'm taking the picture of a string and I want to decompose it onto its modes, I don't see the string going from minus infinity to infinity, and I don't see every single possible real number along the axis. Doing things numerically actually require me to take this beautiful analytic system and break it up first into some finite length, which is something that in sort of numerical work we always call L. I don't know why. Maybe you call it big T if it's time-ordered data, or big L if it's spatial-ordered data. But I know that there's some finite extent to which I can describe the system. And then what's worse is, even over that system, I can't describe it analytically, right? Because it's data. I only have it at certain moments in space or certain moments in time. And so in addition to being able to taking the system and only seeing it for a finite extent, I also only have it finitely sampled. And so in a way, doing a numerical Fourier transform has brought us not just back to Fourier series, but it brings us back to linear algebra, right? It brings us back to this system where I only have a finite number of points. And that's the the sticky point in all of this. And the part that makes you kind of scratch your head is, like, why even call it a Fourier transform? Right? It's really going back to this place where I have a system that's truly finite. And I think before I go on, before I do some of the nitty-gritty of how the computer actually does this, or how the computer stores this, I want us to see that there's a way I can now visualize the fact that I'm only able to probe certain wavelengths with this finite system. right? For example, the longest wavelength that I probably can hope to sample is something whose wavelength is on the order of the size of the actual sample, right? So I tried to draw this red line as being half a wavelength is the distance from 0 to L, or what we used to know is the fundamental frequency of a string, or the lowest omega of one of our systems, right? That's sort of the longest wavelength that I can possibly recover, because if the wavelength is longer than that, my sample is too small to tell that it's actually there. On the other end, if I have a wavelength whose wavelength is comparable to the spacing, then I'm also not going to be able to resolve that, because I don't have enough points along the wave in order to tell whether or not it exists. And so there's already this idea that the sort of longest wavelength, which has a lambda that's equal to, let's see, twice L, right? And therefore it has a k, which is 2 pi over lambda, 2 pi over lambda, which is 2 pi over, look at that, 2L, right? Something like that. That's sort of the smallest possible wave vector that I can resolve in this situation, right? Something that's on the size of that's on the size of the sample. It turns out that well, you'll see in a moment that this 2 actually isn't right. Okay, but I'm only crossing it out because it turns out that that's just our order of magnitude estimate was off by a factor of 2. At the same time, the shortest one, right, is on the order of where lambda now is approximately equal to delta x, right, where delta x is the spacing here, which is, of course, just L over N, right? If lambda is on the order of delta x, right, then k, which is 2 pi over lambda, is equal to 2 pi over delta x. Well, delta x is L over N, which is something like 2 pi over L times N, right? And I get this idea that there's now the longest possible thing that I can see is on the order of delta x. The smallest possible wave vector I can resolve is on the order of L, and the two things actually have this 2 pi over L in common. Okay, and I wanted to point that out here because I can now develop some intuition for the math that's about to come. That somehow the frequencies that I'm able to see in this system naturally happen in units of 2 pi over L, and we'll see in a moment exactly why that should be the case. That should be the case shortly. Okay, so the fast Fourier transform, and the reason why the fast Fourier transform is called a Fourier transform is because I'm going to take my system and I'm going to assume it obeys the wave equation, and I'm going to decompose it onto the same states that I would have had if I had the full analytic Fourier transform. Okay, and that's why we're going to call it the fast Fourier transform rather than the fast Fourier series or anything else, is because I'm going to assume that I can decompose this onto the states of the Fourier transform, these e to the I k x's. Okay, right? I'm not talking about modes from linear algebra or eigenvectors. I'm talking about the actual modes that I get from the Fourier transform. And so if I want to take my continuous Fourier transform and now rewrite it in terms of this discrete set of modes, well, my integral goes back to being a sum. I'm going to leave my square root of 2 pi here. Now I'm going to, instead of evaluating f at all possible points, I'm going to evaluate f at just some set of points. And I told myself I wasn't going to use I. I'm going to use m. Okay, so I'm going to have a set of points m. Those are sampled along my space from 0 to L. And now I'm going to evaluate these at e to the I k x sub m. And where I had a dx, right, where I was doing an integral over x before, I'm now doing a Riemann sum. And so my dx becomes a delta x, which is, of course, just the distance between each one of my points. Okay. Now, I know that because I'm doing this finite sum now on the right-hand side, this means I'm not going to be able to evaluate the left-hand side at any possible value of k, and I'm only going to be able to sample it at some samples of k, which I'm going to call k sub n, and that introduces an n there. Okay, and this now is my idea of doing a discrete Fourier transform. Okay, where I come to realize that I only know what my function is at a certain set of points, which I'm labeling as x of m, and that I only get the Fourier transform. I only get the output of this at another set of discrete wave vectors, which I call y sub n. And I apologize, I'm not real happy with why I called this y. I must have been I don't know. I must have been thinking something different. Let's call this f. Okay, because it's really the f is the thing that I'm putting in, and the f is the thing that I'm getting out. And so I have f of x, which is the function, and f of k, which is the Fourier transform of the function. And I've also forgotten a minus sign. Okay, but now I'm happy with this expression. I've converted my Fourier transform integral into a sum, where I'm summing over a discrete set of points, and I'm getting out the Fourier transform at only a discrete set of modes. Right, and that's how I've reduced this continuous problem into a discrete problem. Now, to find out what the value of those possible modes are, I'm actually going to go back to I'm going to just look at the argument of that e to the I kx. Okay, so I know that the value of x is going to be m times delta x, and of course, if I redraw my space here, so this is 0 and this is L. If I think about each of these points being like m equals 0, m equals 1, m equals 2, m equals 3, I know the value of x here is going to be 3 times delta x, which is 3 times L over n, where n is the total number of points. Okay, and so I can tell where I am by taking m, my index, and multiplying it by how many things over am I going to be. And so if I take the exponent, e to the I kx, and I plug in x as m times delta x, I get this expression. So now I've replaced I've taken care of the x part. What do I do with k? Well, my case of n's, that is, where am I going to evaluate k, is probably also going to be determined by some index n times delta k, right? And so I'm looking at this and I say, well, the thing that I know about delta k, or the thing I know about this exponent, is that it has to be unitless. The only thing that has units here is this capital L, and so my delta k should probably have an L in the denominator, so that way when I plug this in, I get those L's to cancel. And well, since I'm dealing with integers, what we tend to do is we throw a 2 pi in the numerator. Okay, now, there's our 2 pi over L, right? We saw this a couple of slides ago. This was the natural unit that came up when I was talking about wave vectors. But it's also mighty convenient here because my I kx in this case turns into I times m times n divided by n. Right? And all of the L's cancel. Oh, and there's a 2 pi, right? All of the L's canceled, and this thing that I have in the middle is sort of like, it's just indices, right? It's m and n, which are how many over am I, and it's n, which is the total number of points. There's actually nothing in this expression anymore that has anything to do with the physical system. And that's the beauty of the fast Fourier transform, and why the computers are able to do them so quickly is because I can choose units when I look at these exponents that have nothing to do with the physical system, because all of the information of the physical system is encapsulated in my definition of x, or my definition of delta x, and my definition of delta k. Okay, and these are things that when I'm doing the Fourier transform, and this is why FFTs are so hard, is because there's responsibility of the user in order to keep track of all of the units of x and all of the units of k, so that way the computer can do it quickly, and the computer doesn't have to know anything about the actual physical system that you're studying. Okay, and so the things that are hard to calculate, these e to the minus 2 pi I m times n over n, those things are just stored in the FFT. Okay, so the FFT, when it starts up, it calculates all of those once, and then it makes this sum, where I'm taking that exponent and multiplying it by the function, it makes that sum really easy. And actually, there's another thing here for multidimensional things. Instead of summing as n, it goes as log n, blah, blah, blah. That's for Maddie to tell you in computational class, not for me to tell you here. But basically, the computer's able to do this thing very quickly. And this thing, of course, has no information about units in it and has no information about the actual physical system. And that's why it's able to do it so fast. Okay, so the computer's able to do this sum really, really quickly. And so if the FFT is giving us this, which I have in black, and you want this thing, which I have in red, which is the thing that we got a few slides ago for actually, what is the Fourier transform evaluated at this particular set of momenta, well, you'll see that there's a factor, right? This thing. And that's different between the two, and that's what I mean by you have to take care of these things yourself, right? That if you're actually going to give the Fourier transform units, you need to explicitly multiply it by delta x over 2 pi, right? It needs to you need to actually do that to make the thing have any meaning. And so if your Fourier convention is the one that we're using in class, where there's these 1 over the square root of 2 pi's, then you would say something like, the actual Fourier transform evaluated at k sub n is going to be related to the thing that the computer gives me, which we'll call f sub n, times delta x over the square root of 2 pi. Right? And that's just a constant, but it's an important constant because it's a constant that tells me something about the physical system. Okay? Great. Now, but what does that mean for output? Okay, right? Because again, units are really important here. Well, now I'm going to try to represent this sort of as the computer stores things. So on the top, I'm going to have f of x sub m, right? Where these blocks represent the data at each point. And so the first one is m equals 0, which is, of course, x equals 0. So what is the function at x equals 0? The next one is what is the function at x equals delta x, and that's the m equals 1, et cetera, as I get all the way to the end, which is, of course, x equals L. I guess it's x equals almost L, because it's n minus 1, so we'll call it x equals delta L times n minus 1. Okay. So this is my data sampled from 0 to L. When I take the Fourier transform, now things get a little bit weird because my f of k sub n, well, the first one is still going to be k equals 0. Okay? And that, of course, k equals 0, if we go back to the Fourier transform, that's actually the average value of the field. Okay? That's the average. The first bin, n equals 1, is going to have k equals delta k, which is k is equal to 2 pi over L. Easy enough, right? Well, what happens is, when I keep going, k equals 2 delta k equals 3 delta k, okay? K equals, wait a minute, what is k? Now, this is one of those moments where I'm doing this for teaching reasons. Okay, I didn't actually make a mistake. So even though it makes sense to go from left to right, when I do the Fourier transform, I need to know whether or not my k is positive or negative, because for every value of omega, I have a positive or a negative k. And so really, there's a k equals minus delta k that I have to worry about. And now, each computer program does this differently. Okay, most of them put the k equals minus delta k all the way over on the right. And then this is the k equals minus 2 delta k. And this is the k equals minus 3 delta k. And so I have this weird thing set up where the k's sort of come in from the left and the right. Okay? And it stores it in this way, mostly for computational convenience, because you blah blah blah. This is n minus n or whatever. But they collide in the middle, okay? Where this k is equal to 4. This k here is equal to 4 delta k. Of course, you recognize that as n over 2. I happen to have 8 blocks here times delta k. And this block turns out to be really special because it's both moving to the right and moving to the left. Okay? And it turns out with that highest frequency mode, which is at k equals n over 2 times delta k, which is also known as the Nyquist frequency, which is something we talked about when we did finite dispersion relations. When you look at that tiny little wavelength, you can't tell if it's moving to the right or to the left. Okay, and that's special about that particular wavelength. Okay. But when you do an FFT, you have to keep track of the fact that the first half of the blocks are moving to the right, the second half of the blocks are moving to the left, and then this weird one is moving both to the right and to the left. Okay. Now, in the case of a complex field, so if f of x is complex, this actually makes beautiful sense, right? Because I have the same number of blocks, I have the same number of unknowns, and I can, it makes sense to me where all the information goes. In the case where f of x is real, though, which is actually most of the data that we deal with, there are actually some symmetries on the Fourier transform, the FFT, that I have to worry about. I'm not going to get into those with this little video today because I've already talked for too much, but it's worth noting that if the f of x is real, the f of k, of course, is always complex, but you don't generate twice as much information. It turns out there's a symmetry in this system that makes it so that really only half of these degrees of freedom exist. And sometimes, for some FFTs, they actually don't print out half of the information because they assume that you know what the symmetry looks like. We'll talk about that some other day. Okay. That was a very fast introduction to fast Fourier transforms, but basically I wanted to get through the following points. One, you have to keep track of units yourself. And delta k is equal to 2 pi over L. And basically the k's that you can probe go from minus the Nyquist frequency to plus the Nyquist frequency, where the output of this and this are actually the same because computationally I can't tell if the wave is going to the left or the right. Also, whenever you do an FFT, you have to normalize it by hand. The computer doesn't know what the physical parameters are, and therefore that delta x over 2 pi or delta x over square root of 2 pi, you have to put that in yourself. And of course, if I have a complex field that I'm taking the Fourier transform of, things are easier than if I have a real field that I'm taking the Fourier transform of. And that's just something to keep in mind. We're, in this class, going to be doing it in Mathematica, and Mathematica always assumes everything is complex. And so you're going to get the full Fourier transform out, and if you Fourier transform something that's real, you're going to see this beautiful symmetry in the data that you get out. And that's something I think we'll see in our assignment for next week. All right. Sorry that was so long, but it really only scratches the surface on a really interesting topic. Hopefully our intuition for the Fourier transform helps us to understand how the fast Fourier transform actually works.